And what's happening, the reason it's so straightforward, especially in a YAC-like context, is that the information is all flowing up the tree. Okay, they're all synthesized attributes. Right? So if you look at this picture, let's say I have an if node, right? So how do I construct the syntax tree for an if node? I'd say recursively construct the syntax trees for my children. So who are my children? I have an expression, I have a then part, a statement, possibly an else part, right? So I have these three children, of which potentially the else part could be null. But my grammar will tell me that. My parsing process will tell me that. So once I have the syntax trees for my children, I just pull them together, slap an if node above it, and I'm done. So I have my syntax tree, and I can pass that up. So the information is all flowing up the tree. So it's a bottom-up process, all synthesized attributes that makes things really simple. So now, an expression, e goes to e plus e, is simply take the two children, $1, $2, $3, so 1 and 3, slap a plus node on top of it. So make tree is a routine that does the obvious stuff, like malloc of a node, set its node type to plus, and set the children to this one and this one. Here's the if part. So statement goes to if, then an expression, then some statement, then an optional else part. So let's assume that optional else is, here's optional else. It either finds an else and a statement, or it generates epsilon. Correspondingly, the syntax tree it sends up is either the tree for the statement, or it's null. Okay? So opt else is responsible for creating a syntax tree for its child. And because there is no computation associated with this, right? This else is a keyword that relates to the if computation. It doesn't denote any computation performed on this statement. So I don't need to create another syntax tree node. It's enough for this guy to take whatever syntax tree node is created by S and just send that back up. Okay, I don't need a separate node over here. I don't need an else node. The computation is all up here. It's in the if. And conceptually, the computation is evaluate this, and based on the outcome, pick one or the other. Pick one child or the other. Because that computation happens at runtime. So at compile time, I just create the tree to express that, to encode that computation. And let's count 1, 2, 3. So the expression is 3, and then 4, 5. So that's this guy, and 6 is this guy. So this statement creates a tree whose children are, where the root of the tree has type if, and the children, 3 children that are obtained from here, here, and here. And a while node looks like this. So there's this make tree over here, node type, and child 1, child 2, and it does what you would intuitively expect it to do. It allocates space for the tree node. So in this picture, make tree creates this node, or it creates this node. It assigns the type of the node, and then it fills in pointers to the children. Okay, so it fills in the node type and the children. So there's one wrinkle here, which is that my make tree here takes 3 arguments, and make tree here takes 4 arguments. So depending on how you feel about vararg functions, you can set that up as a vararg function, or you can just say make tree will take 4 arguments, and if I only give it 3, then I will explicitly set the 4th one to null or something like that. Either way, I mean this is just sort of straightforward programming, so I don't want to spend too much time on that. Syntax tree nodes. Now I have $, each YAC symbol is returning a syntax tree node. So I have to go and fiddle with the % union. Okay, Steve?
I don't know off the top of my head, but does C minus minus say that you can have at most one statement after if or else?
Does C minus minus allow you at most one statement after an if? The language says there's exactly one statement for here, but of course, I mean that's true for C as well, right? If you want to have more, you've got to bundle them up inside braces, a compound statement. And that's exactly what you have in C as well. So what you would, so how would you handle something like this? Let's pursue the previous example that we have and see how might we do this other kind of node. So intuitively, at a top level, I can say a statement can go to a compound statement within braces, right? Now, I have forgotten what the grammar rules for this look like. What do they look like? You guys have the grammar. I don't remember what the grammar rules look like. Statement list. Okay. So this is statement list?
No, it's stuff inside the bracket.
Okay. Goes to what? So it goes to something. We'll come back to that. What should the syntax tree for this look like? So I don't know. Someone want to elaborate and put that into a picture? You want to do it? Go ahead.
Just have a bring down here, close whatever this is. It's just got like a child. It's the same thing.
So let's suppose I have three statements in my list: S1, S2, and S3.
And this guy points to nothing. Call that as nothing.
Okay. So where are the children? Where are the trees for the statements themselves?
Over here.
Right. Yep. Thanks. So that's exactly right. If I have a statement list, this can have arbitrarily many statements in it. Correspondingly, my syntax tree is an arbitrarily deep list over here. And these are the syntax trees for the individual statements, right? So this might be, just elaborate on this a little bit. Maybe this is an if, which has its own 3 children. And maybe this is an assignment statement, which has its own children. And maybe this is a while, which has its own children. And the while, the second child of the while, is a statement. And that might itself now be a statement list, which has, like Brian drew. So you can have trees for the children. So that's what these things end up looking like. So the data structures can get big and complex looking. But if you think about it carefully, you can decompose them into units that are not that complex. Okay, it's just that the composite can become a large data structure. It's actually interesting, in 352 right now, we're programming up graph structures. Okay, so you have nodes, and these nodes have pointers to other nodes. And we're looking at, we're implementing graph algorithms like, let's read in a graph that, where you talk about what the edges are, what the vertices are, and then ask questions about what node's reachable from what node, or spanning trees and so on. So in a lot of ways, the structures that they're looking at resemble something like that, though not quite as complex, but similar sort of deal. Okay? Just structs and pointers to other structs, and then you process them. So that's syntax trees, right? And as I said, the reason syntax trees appear in the current assignment for you guys is not because it's an essential part of the assignment. And I said so as much on Monday. I won't be testing for it. But because the last assignment, assignment 4, is so much work, if you are able to move some of that, pull it into the current assignment and do it now, that'll save you that much time down the road. So that's the reason I've put syntax trees into the current assignment. But as you can see here, syntax trees aren't that much, conceptually, they're not that much work. Now, once you finish this assignment, let's suppose you did the syntax tree part as well. So let's suppose that when you turn in your code on Sunday, when you turn your code in on Sunday, you have the type checking happening and you have the syntax trees in there. Then, for the code generation part, you become essentially completely free of the parser itself. So what your parser code now looks like is something like this. Right? In your Yak parser, each production is associated with some rules that manipulate the syntax tree. So then, you also have rules for the function at the top level for the function. And this looks like something like type, ID, parameter list, and then braces, decals, statement. Then at this point, you have the syntax tree. The syntax tree has pointers into the symbol tables, local and global. At this point, I can say generate code using the syntax tree. So what goes in over here is the syntax tree. And the generating of code, the actual assembly code that is put out, is now completely separated from all of the other stuff, right? So all of this stuff does not need to be involved with code generation, because the code generation simply traverses the syntax tree. The syntax tree specifies what the computations are, right? It says, here's a plus node, here's a multiplication node, here's a while node, here's an if node. So you know what the computations are by traversing the syntax tree. And therefore, you can generate the code. And you don't have to insert code generation stuff all through the parser. So the code generation process becomes independent of the parser code. Okay, so that's one comment. The other comment is that the way I have over here, $$ is returning, the way I've shown it, a tree node. Right? So each symbol over here is returning a tree node. Now, from your type checker's perspective, getting a tree node back is not terribly useful in itself, because your type checker wants to know about types. Right? So maybe, so this is optional. There's a lot of different ways of doing this, but maybe what you have here is that the node that the symbol returns is a syntax tree node that also has the type associated with that node. Here's what I mean by that. If I have an expression x plus y, if I was doing, sorry, not x plus y. Let's say e goes to e plus e. Okay. If I was doing pure code generation, then I would have, I'm sorry, what I meant to say was if I was doing pure type checking, then I would have something like $= equals int. that the type over here is the result of carrying out this computation, and in C minus minus, chars can get promoted to int. So regardless, this is an int. So this would be for pure type checking. For syntax trees and type checking, what I would do is $$ would be equal to make tree. So I would create a tree node of some kind. Here's what the tree node might look like. Okay, so this is what the tree node might look like. The tree node would have the node type. The node type here is plus. It would have pointers to the children. So these are children in the syntax tree. And it would have an expression type, which is equal to, in this case, int. Okay? So let's think that through briefly. The node type tells you what sort of node it is. Is it a plus node? Is it a multiplication node? Is it an if node? Is it a while node? It's what we have over here. The expression type says, at runtime, when I compute the value, this is the type of value I get. And in this case, it says the type of the value is int. Okay? So I might have a whole bunch of different tree nodes. Some of them have node type plus, some of them have node type multiplication, some of them have node type unary minus, some of them have node type, I don't know, divides, whatever, right? And they might all have expression type int, or some might have expression type char. Okay? So is that distinction make sense? So now, if this is what $$ is set to, a structure of this sort, so each grammar symbol returns something that has a syntax tree as well as type information. For type checking purposes, you check the expression type field. For code generation purposes, you use the rest of the tree node. Okay? Question? No. Yeah?
Just be another part of the node, though, right?
That is another part of the node. That's exactly right. It's just that that's information that's there for the type checker. So the next item on the agenda is low-level intermediate codes. We just talked about high-level representations. Syntax tree is sort of the canonical one. There are other representations, but this is just as good a one as any. With low-level IRs, the instructions look a lot like machine-independent assembly code. So they sort of kind of look like assembly code. The syntax might be, different, depends. So they look like something is assigned, something off something. In this case, I have 3 different, operands, if you will, destination operand and 2 source operands. But sometimes I might have just 1 source operand. Sometimes maybe I don't have any source operands. But it's sort of kind of like that. But the key thing with 3 address code, the key thing is that I don't allow more than 1 operator on the right-hand side. I allow at most 1 operator. If I did allow multiple operators on the right-hand side, then it begins to look a lot like C, right? I mean, I can say x plus y times z divided by w, things can get arbitrarily complex. I don't want that. The whole point here is to slowly migrate to something that is closer and closer to the target machine. Okay, so this is an intermediate representation that is closer to the target machine in the sense that expressions are now only allowed to have at most 1 operator. That's sort of kind of like what assembly code gives you. Each instruction gives you 1 operation. Okay? So that's all well and good, but the obvious question this raises is, well, if the source program is allowed to have multiple operators on the right-hand side, then what do I do with them? So I'll fall back on my canonical friend, ID plus ID times ID. So let's say X plus Y times Z. Here's an expression. Okay, here's an expression in a program. How do I encode this, given that I'm not allowed to have built-up expressions? So think about it for a little bit, not very long even. You find that you don't really have a choice, right? If I'm not allowed to have multiple operators on the right-hand side in my 3-address code, in my low-level intermediate code, then the only thing I can do is to use multiple intermediate instructions to evaluate this. So I have to compute this guy. So I have to compute Y times Z and store that value someplace into some scratch location, and then take that scratch location and add that, and that's the value of this expression. Okay? So by going to 3-address instructions and using this simplifying restriction that I'm allowed at most one operator on the right-hand side, what that buys me is that it gets me closer to the kind of instructions that I actually get on machines, in the assembly code. So that's a good thing. Nothing in life is free, especially in compilers, especially in computer science. So what I have to pay in return is that my programs become a little bit more involved, because now I have to deal with this business of these temporary, these scratch locations where I have to stash intermediate computation results. And those things are called temporaries. So a temporary, or temp, is a compiler-generated variable. These temps live in the symbol table, just like any other variable does. And a good compiler will generate the same regardless of whether the temp was introduced by the compiler or whether the temp appeared in the source code. Because this sort of code could be just as easily have been written in the source program by the programmer, right? So a good compiler will treat those identically and produce pretty much identical code. So here's an example, right? So there's my source program with all kinds of complicated built-up expressions. And my target program, the 3-address program, flattens these expressions out. So Y times Z gets computed into a temp. X plus, well, that's supposed to be temp 1. X plus temp 1 gets saved into temp 2. This X times Y gets computed into temp 3. Temp 3 plus Z, so that should be temp 3. Temp 3 plus Z gets computed to temp 4. So you can see how those built-up expressions are getting flattened out. Right? And now I do my comparison between temp 2 and temp 4, and so on. Question?
Can you make sure that the user doesn't assign one of the things that you created to some other value?
That's absolutely right. So Brian's comment was that the compiler has to be careful that temp 1 is not the name of a variable that's already in the program. And I know that I write code that have TMP1 and TMP2. That's not an uncommon way of writing scratch variables, right? The programmer wants to emphasize that this is a scratch variable by giving it a name that resembles a scratch variable. So you have to make certain that the compiler doesn't inadvertently introduce problems like that. Now, let's think for a little bit about how one might do that. And that relates to what we have to do with these temp variables. Okay? And since in the project you guys are pretty close to code generation anyway, this is a reasonable time to think about it. What you're going to do with these temp variables is that eventually, at some point, you will have to allocate space for them. Right? So if I think of this computation, just think of how you might implement this computation. For a second, let's not worry about compilers. Just imagine that you have to encode this computation in MIPS assembly. Well, you would compute Y times Z, put it somewhere, then take that value, add it to x, and so on, right? I mean, you carry out computation sort of kind of like this. At this point, I'm not going to distinguish between whether these guys live in registers or in memory or what. That's a decision that can be made later. But the point is that I need to set aside some space, which might be a register, might be memory. But I have to set aside some space for this guy. And I have to set aside some space for this guy, and so on. So we have to set aside space for temps. Because when I carry out a computation, that result has to be put someplace. Again, could be a register, could be memory. That's a final code generation issue. For now, just conceptually, that has to be put someplace. We also have to set aside space for these source level variables, right? So someone somewhere has to decide this variable needs space allocated, this variable needs space allocated. It should be allocated on the stack. Something else might be allocated in global memory. I have to figure out how much space I need to allocate based on the type and all of that. So it makes sense to put all of that decision making, all of that logic in one place and have all of the space allocation decisions happen in the same way. What that implies is that you want to stick the temps in the symbol table, because the space allocation is going to use the symbol table to figure out what the variables are and what the types are, what the scope is, and therefore where and how much space to allocate. Okay, so you're going to put the temps in the symbol table. There's nothing fundamentally different about temps versus regular user variables. So that then raises the question, okay, if I put them in the symbol table, I have to make sure that I don't get inadvertent name conflicts. One way you can do that is, since the temp is generated by the compiler has complete control over the name of the temp. So you can give a temp a name that could never arise in the source program, right? So when I wrote my compiler, I had the name start with a $, because I know that my lexical analysis, my scanner, will never allow variables with names like $x and $y or $12. Right? So a scheme like that will guarantee that temps can never conflict with user variables. But it's an important point to keep in mind. So looking ahead to the next assignment, assignment 4, here's a intermediate instruction set. So this is an A3 address instruction set. For your assignment, you're not required to use this instruction set. There's no particular requirement for this. I'm putting this up as sort of a representative set of operations at the intermediate level. There are some things in here, convert A to B, so convert int to float, that actually don't appear in the, there's a corresponding document on the class website, an intermediate code. And some of these don't even appear there. But the reason I'm bringing this up is that, let's actually go look at that. Documentation. So there is this 3-address intermediate code. And this one, there's a few of them over here. There's no particular requirement that you need to use this. You're welcome to use whatever intermediate instructions you want for your project. The only reason I've put this up is that I felt it important to give you some guidance on how intermediate instructions get mapped to final code MIPS instructions. And there's this document over here that says, here's how the translation happens. So there's this particular document. And this talks about, whoops, what happened? That can't be right. Let's look at the PDF version. So there's a document that says, here's how the translation happens, and here's what the declarations look like, and here's what here's the instructions that are generated for a load, and so on. Okay. So that's the only reason that I've put up that intermediate instruction set, the 3 address set. So you can choose different instructions if you'd like, and I don't have any particular issue with that one way or the other. But if you want to use some different instructions at the 3 address level, then you need to figure out the translation to MIPS assembly level. That is not particularly difficult, okay, because as we saw in these examples, the kinds of operations that you see, like if, some comparison, go to some label, carry out a binary operation, carry out a unary operation, do a copy, okay, indexed assignments, indexed lookups, dereferencing, pointers, and so on. These are all things that are relatively straightforward elementary operations, right? So if you want to do something a little differently, that's okay, and go for it. If you have questions, come and talk to me, and we can talk about it. But you have to figure out the translation to MIPS assembly. That's all, okay? Since I'm almost out of time, I'm going to stop over here today. And on Monday, we'll pick up from here, and we'll talk about how you represent 3 address instructions and how we actually do code generation. So that's what we'll discuss on Monday. See you guys then.